All right, so this is Math 146. We're still in section 7.1, sequences. And last time we really talked about how to define sequences. Remember, it's just a list in some kind of a specific defined order. And we talked about a little bit about how to get to the nth or general term of the sequence. And we also talked a little bit about this thing which is called a factorial. So now we're going to talk about something which is called a recursive. I can spell it correctly, recursive sequence. And the idea of a recursive sequence is that the sequence is generally based upon something that has already happened in your sequence. So usually the general term is going to be based upon something that's happened with previous terms. For example, if I tell you that s of 1 is 1, and I am trying to find the sequence based upon that, where s sub n is defined to be s times s sub n minus 1. Well, then that means that every value that I'm going to plug in for n after 1 is going to be dependent upon something that has already happened before, because the n minus 1 term literally means the term that was before this. So for example, if I want to find s sub 2, that literally is, by the definition here, 2 times s sub, plugging in 2, you would get 1. That should be a times, not a minus. And that's an s, not a 5. I hate s's because they look like my 5s a little bit. So then you get 2 times the previous term. Well, s sub 1 was defined to be 1. So you get 2 times 1, which is 2. And then s sub 3 is now defined to be 3, because that's the n, times s sub 2. So now I'm going to take what I got for s sub 2, which was 2, and multiply it by 3, which is then going to give us 6. S sub 4 then is going to be 4 times, come on, times s sub 3, which is 4 times 6, which is 24, and then maybe s sub 5, which would be 5 times s sub 4, or 5 times 24, which is 120. And the important thing about this is to recognize that this is really, if you look at these numbers, 1, 2, 6, 24, 120, those are factorials. Okay, so this would literally be n factorial as the actual sequence of terms. And again, you would just kind of have to recognize that 1 is 1 factorial, 2 is 2 factorial, 6 is 3 factorial, because remember it's 3 times 2 times 1, and then 24 is 4 factorial, because that is 4 times 3 times 2 times 1, and so on. 120 is 5 factorial, and so on. So it's good to start recognizing when you see that pattern of 1, 2, 6, 24, 120, that's a factorial pattern. It does help. Probably one of the most famous recursive sequences is the one that looks like this. So the first term is 1. The second term is also 1. And every term after that is going to be defined by its previous couple of terms. Trying to erase here. Why won't this work? Oh man, if you saw that little fading there for a second, I thought literally everything was going to crash on me and we're going to lose the whole recording, but that didn't happen. So anyway, I apologize for that. So in this case, again, this is a really famous sequence. The first term is defined to be 1. The second term is also defined to be 1. Every subsequent term after that is going to be defined by u sub n minus 2 plus u sub n minus 1, or basically taking the previous 2 terms and then adding them up. So the third term would be taking the previous 2 and adding them up. So I'd get 1 plus 1, which is 2. The next term would be taking the previous 2 terms, which now is going to be this one, and adding them up. and we'll get 3. The fifth term will be taking the fourth and the third term and adding them up, and we would get 5. The sixth term is going to be taking the fourth and fifth term and getting 8. We'll do one more. The seventh term would be taking the 5 and the 3 and get 13, and that pattern would keep on going. This is what is known as the Fibonacci sequence. And again, it is one of the more famous sequences, and it has a lot of application to a lot of stuff that actually happens naturally throughout the world. So based upon natural sciences, you will see a lot of things that happen with the Fibonacci sequence. It's a really cool one if you want to delve a little bit deeper into it. But that's the idea about recursive sequences. So the recursive sequences depend upon previous terms in order to get the current term. All right, let's talk a little bit about notation, because if we want to take and add some of these numbers up that we've gotten, we're now creating something which is called a series when you start to add them up. And to do that, you don't want to literally have to write out a sub 1 plus a sub 2 plus a sub 3. So like doing this is going to be kind of a pain to do every single time. So we've come up with a shorthand notation, which is called sigma notation or summation notation. And the reason we call it sigma notation is because we use the capital Greek letter sigma, which looks like this, in order to indicate we're actually going to take a sum of something. So sigma was chosen because of the S sound, and it's going to indicate a sum. And what you're going to take the sum of is all of the general terms, all of the general terms of the sequence, starting at some number and then going all the way up to whatever other number you want it to be. So if I want to start with the first term of the sequence, I would just simply let my k value be 1, because that would give me a sub 1. And then I would add all the terms all the way up until whichever one I choose. Well, for right now, we're just going to call it n. So that would literally be a sub 1 plus a sub 2 plus a sub 3. And because we don't know what n is, we put the dot, dot, dot in there and write it all the way up to, in this case, a sub n. And that would literally be a way to say I'm going to add up all of the terms all the way up to whatever I choose n to be. And that's the general idea. So just a real quick example here of what that would look like. Let's just say that I wanted to find the sum, and probably the hardest part will be learning how to write that sigma notation relatively quickly. I want to find the sum as k goes from 1 up to n of the sequence 1 over k. Well, simply that is, let's start with 1. So you put in 1 over 1, and then you go to 2, so 1 over 2 plus 1 over 3. And obviously we don't know what n is, so we just kind of put a plus and then dot, dot, dot. Then we do that all the way up till we get to the nth term. And that's kind of how you would write that out. Now, if you knew what n was, let's say n is 6, then you would just simply plug in 1, 2, 3, 4, 5, and 6, add up the values, we'd be done. Okay, and that's pretty straightforward. But now let's say we have to go the other way around. Now let's say we are given a bunch of terms and we need to write the summation notation for that. So let's say that we are given 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to 9 squared. And that's actually where it stops, because there's no n's or anything in that. So this one's a little nice, and the fact that it does actually stop someplace. So the sigma notation, because we have to write that now, would look like, well, k is going to start with 1, because what you should notice is that the bases here are the things that are changing. The exponent is staying the same, so all these bases are changing. So k is going to start with 1 as the base. We're always raising the base to the second power. So that's really the general term for your sequence. And we know that k is going to stop at, in this case, at 9 because that's what it says on our, that's what we were given in our sequence of terms. So that would be the sum as k goes from 1 up to 9 of k squared. And then literally you could add all these things up, but that's not what we're asking you to do. We're just asking you to be able to write the sum notation here. Let's do one more example like that, just a little bit, with a little bit more difficulty to it. So let's say that we are given 1 plus a half plus a fourth plus an eighth plus dot, dot, dot. Now in this case, I'm actually going to give you the general term. But if you weren't given that, you might have to figure it out. So there's your general term. And all I want to do is write the sum. So the sum notation is going to start with k equaling 1. And they've given us the general term, which is really nice. So that's 1 over 2 to the k minus 1. Only thing we have to figure out is what does k end at. In this case, k is going to end at n because it doesn't have a number down there. It's got an n, so it's going to stop at n. And that's a way to write the summation notation for that specific one. There are a bunch of properties of sequences which are going to be kind of important, especially once you get to calculus. And these are relatively easy ones, I think, to be able to figure out. So if we were to have a sum, let's write this down, properties. If we were to have a sum of whatever it is from 1 to n of c a sub k, where c just simply represents a constant. Well, basically that would be like saying I have c times a sub 1 plus c times a sub 2 plus c times a sub 3 all the way up to the nth term. Well, you could very simply factor a c out of that. And then you would have a sub 1 plus a sub 2 plus a sub 3 and so on. So the general idea is that I can factor the c out and then take the sum of just the a terms. Or I can pull a constant out to the front of the sum, take the sum of the terms, and then multiply by that constant. So it makes it a little bit easier. You can factor a constant out to the front of the sum. You cannot do that if it's still got a k in it, if it's not constant. But if it is just some number, some constant, you can pull it out to the front. The next two I think are also relatively intuitive in the fact that if I have a sum of a sequence of a sub k plus or minus some b sub k.
Okay, I found this on the web. Forgive me a sec.
That's what I get for saying the word sequence or series, not the word that my phone thought it was. I'm actually curious to see what it thought I was asking for. Anyway, if I have this sequence where I've got a sum of a sub k plus or minus b sub k, well then you can split up the two sums through addition or subtraction. Oops, I don't know why I put an infinity on top of there. I do know why, but it has nothing to do with what we're doing. To be the sum of a sub k plus or minus the sum from 1 to n of b sub k. So you can take the sums of the two separate sequences individually and then add them together as well. So you can do that. There are some formulas that we probably should be aware of for finding sums. The first one is if I were to simply take the sum as k goes from 1 to n of a constant. Well, the idea is pretty simple because I have nothing to plug k into since there's no k's in the sum. I'm going to have simply for my first term would be c. My second term would also be c. My third term would be c, and so on, all the way up till I get to the nth term, which is also a c. So basically the idea is, because I would have n of those, I would have c times n. So if you're going to sum a constant, you're just going to figure out whatever n is and multiply that c value times n. That's your sum. The next one is k goes from 1 to n of k. Now I actually do have something to plug into. So that would actually be 1 plus 2 plus 3 plus 4 all the way up until you get to n. Okay, and the sum for this is n times n plus 1 over 2. So the way I like to think about this one, because this one you can kind of see, is that if you were to take the first and the last term of this, you would get n plus 1. So if you took the first and the last term, that would be n plus 1. If I were to take the inside of this, which I didn't write down, if I were to take the 2 and the term right before n, well, that would be 2 plus n minus 1. But that actually simplifies by combining like terms to n plus 1. If I were then to take the next inside two terms, the 3 plus n minus 2, so I'm just kind of working my way backwards from the end, that's also going to be n plus 1. So ultimately you're going to get an n plus 1, but you're only going to get that for half of the number of terms that you have. For example, if I went from 1 to 100, I would add up 1 and 100 and I would get 101. I would add up 2 and 99 and I would get 101. But that's not going to happen 100 times because we're taking numbers from either side. It's only going to happen half of that. It's going to happen 50 times. Well, that's where this piece right here comes into, oops, I did not mean to use the eraser. That's where this piece comes into play. The n divided by 2 says we're going to take half of the number of terms that we have and multiply it by n plus 1. Okay, if none of that really made any sense to you, you can always just choose to memorize the formula, but hopefully that does make a little bit of sense as to why you're getting n times n plus 1 over 2. The other ones here, I'm going to show you what they are. I am not, however, going to show any kind of a proof for those. A little bit more difficult and lengthy, but still interesting. You could have the sum from k equals 1 to n of k squared, and that's going to ultimately end up being n times n plus 1 times 2n plus 1, all divided by 6. And then the last one that we will actually use, obviously there's more of them, we could keep going. Oops. That would be k cubed, which is going to end up being n times n plus 1 all over 2 squared. Or some people like to write it as n squared n plus 1 squared over 4. Same thing, just distributing the square in. Either way is perfectly fine. Again, I'm not going to prove the k squared or k cubed ones. If you really wanted to dig into that, you could. So those are just good formulas to know. That way now if I know, for example, for any of these, if I've got something that has a k squared in it, and I'm looking for the sum from k equals 1 to 7, I would just plug 7 into all of the n's right there, and I would know what my sum is. It's not as necessary if you're doing it for smaller numbers, but for larger numbers, this helps a lot instead of having to write out every single term. So, for example, we're only going to do one example here because this will incorporate a bunch of things. Let's say that we wanted to find the sum as k equals 1 to 24, so the first 24 terms of k squared minus 7k plus 2. Well, we can incorporate a whole bunch of those properties all at once because this can be written as the sum as k equals 1 to 24 of k squared minus, now I can pull that 7 because it's a constant out to the front of the next sum, And we're using the subtraction property here to separate the sums. And then that would be the sum of k from 1 to 24. And then the last one is simply separating through addition the sum of 2, which is a constant. So we've got a bunch of properties we can now use. So if we go back to our summation formula, k squared, I know that that's going to be n times n plus 1 times 2n plus 1 over 6. So the first one is going to be, if I, knowing that n here is 24, it's going to be 24 times 24 plus 1, which is 25, times 2 times 24, which is 48, plus 1 is 49, all divided by 6. And that's the sum of that first part, minus 7 times, and then the k is going to be the n plus 1 over 2. So that's going to be 24 times 25 divided by 2. And then the last one is probably the easiest one. It's just a constant, which is going to be a constant times n. So it's 2 times 24. And that's going to be the way you would find your sum. I'm not going to run through actually like breaking down all of the math here, but it actually works out to be 2,848 when you simplify all of that. So much easier probably to break this thing up than to actually plug in 1 through 24 into this thing right here and write out all of those terms just using these formulas. Probably the easiest way to do that. And that is basically how you would find the sum of a given sequence given a specific number of terms. Okay, that is enough for this video. We have finished 7.1. We've got 2 more sections to go. We're going to talk about geometric sequences and series, and then the last thing is the binomial theorem.